Okay, so this is June 2009 and this is the CA paper of the old specification. Question number 11 is based on our atomic structure topic, and it asks us to draw an arrow on the diagram representing an energy change. Now, the important thing with these questions is that notice here at the bottom they are worth a lot of marks. There's 3 marks here for drawing one arrow. And that seems very strange, but there are 3 pieces of information in this question that help us to know which arrow to draw and between which lines. So we'll get that information from the question now. So I'm going to underline these parts in different colours. Okay, so it says the energy change associated with the lowest frequency line, okay, that's one part, in the ultraviolet emission spectrum. Okay, so there's 3 different pieces of information there. And we're going to work our way backwards. So, what does emission mean? Emission means that the energy is going to be given out from the electron as it falls from a higher energy level to a lower energy level. And so the first mark you get is for drawing an arrow in the down direction. So our arrow is going to be going down. So that's the first thing we know. Second thing is then the ultraviolet part. Well, what do we know about the ultraviolet emissions? Is that ultraviolet emissions always go down to energy level n equals 1. So they can come from any other energy level. They can come from energy level 2, 3, 4, 5, but they have to end up at energy level n equals 1. So we know that our arrow is going to go down to level 1. Okay, and the last bit of information we have is that it's the lowest frequency line. So it is going to be the energy change that has the lowest possible energy, the lowest possible frequency, because we know that frequency is proportional to energy level. So it's not going to be from n equals 4 down to n equals 1. It's not going to be n equals 3 down to n equals 1. It's going to be from n equals 2 down to n equals 1. And so now we finally have enough information to draw our arrow. So we are drawing a single arrow down from n equals 2 to n equals 1. You can see at the side where your 3 marks come from. You get a mark for drawing an arrow in the downward direction, and mark for starting your arrow at n equals 2, and a mark for ending your arrow at n equals 1. And just to complete it, sometimes you are asked to label the energy levels, so I would do that just to be complete. So that's n equals 2, n equals 3, and n equals 4. So you can see our arrow is going from n equals 2 down to n equals 1. Question 12 is talking about dipoles within a bond. And for this question, all you need to do is to decide which of the 2 elements within the bond has a higher electronegativity. So the first one has been done for us. Chlorine has a higher electronegativity than carbon, and so chlorine has the delta negative charge. That means that within the carbon-chlorine bond, chlorine attracts the bonding pair of electrons with a stronger force, and so the electrons sit slightly closer to the chlorine than the carbon, and so that gives it a slightly negative charge. Okay, then with oxygen and hydrogen, which has the higher electronegativity? Well, that is oxygen, and so our electrons sit slightly closer to the oxygen. You don't need to draw the electrons in, so that means that it's going to have delta negative, hydrogen is going to be delta positive. Chlorine and bromine, Well, if you remember your electronegativity rules, the easiest way to remember it is that fluorine is the most electronegative element, and it sits in the top right hand corner of the periodic table. So electronegativity increases as you go across a period and up a group. So in our halogens, fluorine is at the top, then we've got chlorine, bromine, iodine and astatine. And so that means that chlorine is going to have a higher electronegativity than bromine. And so our delta negative sits on our chlorine and our delta positive on our bromine. And then finally, nitrogen and oxygen. Again, if you think about our electronegativity rule, the order of period number 2, we've got carbon, then nitrogen, then oxygen, and then fluorine. And so oxygen is going to have a higher electronegativity than nitrogen. So our delta negative will sit on our oxygen and our delta positive will sit on the nitrogen. Question 13 is a calculations question, and it is important that you do read the questions. You can see that it's quite wordy here, but it's important that you read the question to make sure you don't miss any information. But when the calculation is divided up like this, usually the headings will help direct your calculation. So don't look at the question, see lots of words and be put off by it. Really, it can be quite simple, and it helps when the question is broken up into these different parts. So just take it one step at a time. Don't think of the big picture. I have to get what is the mass in grams of these 60 molecules. Don't think about that. Just think, first of all, about the individual steps. So the first step is calculate the relative molecular mass, which you're more than familiar with. So the relative molecular mass, we know our formula is C11 H18 O2, and so the RFM of that is going to be 11 times 12, as 12 is the mass of carbon, plus 18 times 1, as there are 18 hydrogens, and there are 2 oxygen molecules, and so that is 2 times the mass of oxygen, which is 16. So 11 times 12 is 132, plus 18 plus 32, and that is equal to 182. Is the relative molecular mass. Just be careful that you put things into your calculator correctly. So what is the mass of 1 mole? Again, that's very straightforward. The relative molecular mass gives us the mass of 1 mole in grams. So the mass of 1 mole, another way we can put that is the molar mass. And the molar mass, by definition, is the RMM of a substance in grams. So if our RMM is 182, then it's 182 grams. If you really wanted, you could do mass equals N times RMM, which would be 1 times 182 is 182 grams. But the relative molecular mass gives you the mass of 1 mole in grams. The next part of the question asks for the mass of 1 molecule. Well, we have the mass of 1 mole, and we know that 1 mole is equal to Avogadro's number of molecules, and that is 6.02 times 10 to the 23 molecules. And we know that 1 mole is equal to 182 grams. So 6.02 times 10 to the 23 molecules are equal to 182 grams. So if we now want 1 molecule, we need to divide 182 grams by 6.02 times 10 to the 23. And putting that into your calculator, you should get 3.02 times 10 to the minus 22 grams. Okay, so that's the mass of 1 molecule. And so the mass of 60 molecules is just going to be, so 60 molecules is going to be 60 times this number, if that is the mass of 1 molecule. 60 times 3.02 times 10 to the minus 22 grams, which is equal to 1.814 times 10 to the minus 20 grams. Okay, just make sure you include your units. Sometimes they are accounted for, sometimes they're not accounted for. Because the question says in grams, that essentially gives you the units, but make sure you include the units just to be sure. So again, don't be put off by a long question. You can see that was fairly simple. Question 14 is a question on giant covalent structures, a question that you would have been capable of answering at GCSE. The first part of the question, this is all based on boron. So compounds of boron form giant covalent structures like boron nitride. So the key thing is that boron nitride has a giant covalent structure. And we know 2 substances that have giant covalent structure, and that's diamond and graphite. So it's going to have similar properties to diamond and graphite if it has a similar structure. And we also know that quartz has a giant covalent structure, but it's not quite as common an example. So why is diamond so hard? Diamond is so hard, if we think about its structure, if each of these dots represents a carbon atom, each carbon atom is connected to 4 others tetrahedrally. And that structure goes on and on and on. And then that'll be connected. And so it continues right throughout the lattice. And that is the key things. The 2 things that you need to mention here are that those carbon atoms are connected by these strong covalent bonds. Okay, so the first point is about the strong covalent bonds. Strong covalent bonds, that's 1 mark. And the second mark is for saying within a giant structure or throughout the lattice, that extend throughout the lattice, that sort of idea. So it's the strong covalent bonds that make it so hard, but the fact that those bonds go on and on and on within the giant structure. Because you obviously have strong covalent bonds within water molecules, but it doesn't have a giant structure, it's just those individual molecules. But each of these are a really strong covalent bond, and that lattice goes on and on and on, so it's very difficult to break up that lattice. But on the other hand, we have diamond, which again is a giant covalent structure, but it is soft. And why is that so? Well, again, we need to think about the structure of graphite. I'll zoom in here so we have a bit more space to draw. So graphite exists as the carbon atoms in hexagonal rings. So each carbon is joined to 3 others. They're just connected to 2 at the minute. So that forms a hexagonal ring, and then we form another hexagonal ring off of that as well. And graphite exists in these layers. So if that is one layer, then there will be another layer underneath formed again of the carbon atoms in hexagonal rings. So these layers form, and there will be another layer underneath and underneath that. And these layers are held together by weak attractive forces. So if each carbon atom uses 3 of its bonding, if its electrons for bonding, then each carbon atom has 1 electron that is lost as delocalized electrons that are situated in between the rings, and they're free to move about, and that's why graphite can conduct electricity. But it's the attraction between those layers that holds graphite together, but those attractive forces are weak. So let's think about how we're going to explain why graphite is so soft. What we want to say is that graphite exists as layers. So you get a mark for saying layers of carbon atoms, you could say, but you don't even need to mention that, but we'll put that in anyway. So layers of carbon atoms, and these layers can slide past each other. So layers of carbon atoms that can slide past each other. And that gets you your second mark. That's what makes it so soft, because these weak attractive forces between the layers, they're so weak that we can overcome them very easily, so the layers can slide past each other. And that is the other way you can make the second point. You can make mention of the weak van der Waals forces between the layers. So the first, you get 1 point for mentioning the layers, exist in layers, and then either saying these layers can slide past each other, or there are only weak van der Waals forces between the layers. But again, that's saying that then they can slide past each other. And the last part of the question says, state one other property apart from hardness which you would expect a boron nitride to possess. So going back to the start of the question, and tells us that boron nitride forms a giant covalent structure. So as I said at the start, boron nitride is going to have properties similar to that of giant covalent structures. And so what they're looking for here is any other property of a giant covalent structure. So some examples could be a high melting point or boiling point. Obviously write that out in full. Giant covalent structures also tend to be insoluble in water because their molecules, their structures are non-polar, and so there's no attraction to the water, and they also tend to not conduct electricity. Obviously graphite is our exception of that, but does not conduct electricity. So any other property of a giant covalent structure. Part B of question 14 goes on to talk about more boron compounds. Now boron isn't an element that we would have particularly studied in Module 1, but this question takes into account different aspects of the course. And for a lot of this, and we'll see in the first 2 parts of the question, it's just about reading the information from the question. So it says the boron and carbon combine with fluorine, so they react with fluorine and form fluoride compounds. Boron forms boron trifluoride and carbon forms carbon tetrafluoride. So it asks us to write an equation for the formation of boron trifluoride from boron and fluorine. Okay, again, not an equation you would have learned, but something you should be able to write from the information in the question. So we've got boron, which exists, its symbol is B, and then we've got fluorine. But remember, fluorine is a diatomic molecule, and so you must write it, when it's in its element form, you must write it as F2. React to give us boron trifluoride, BF3. Okay, now we need to balance it. So we list the elements that we have on the left hand side, and then we write them in the same order on the right hand side. So we've got 1 boron and 2 fluorines on the left hand side, 1 boron and 3 fluorines on the right hand side. Now with the fluorines, to balance fluorines, we could go up step by step by putting 2 in front of your fluorine and so on, but we can see that we've got 2 on the left hand side and 3 on the right hand side, and so we can fix that by putting a 3 in front of the fluorine here. That's going to give us 6 fluorines on the left hand side, and then we've already got a 3 here, and so we can put a 2 in front of there to give us a total of 6 on the right hand side. But we also need to change our number of borons, because that big 2 in front of the BF3 has changed our number of borons as well, and so we've now got 2 borons on the right hand side. That means we now need to change our number of borons on the left hand side. That's quite easy. We just put a 2 in front of the B here, change our list, and you can see that our equation is now balanced. So we can write it into the answer box as balanced. So it is 2B plus 3F2 gives us 2BF3. Now it is important that you balance those equations correctly. You will get a mark for writing the correct equation and then a mark for balancing. So make sure you don't miss out on easy marks by just simply making a mistake in your balancing. So take a separate page and do out your balancing numbers as we did there. Now we have to write another equation again worth another 2 marks. So now it's the formation of carbon tetrafluoride from methane and fluorine. But there's an added sentence in here which tells us that the other product is hydrogen fluoride. But again, we're just writing an equation based on the question, the information given in the question. So write an equation for the formation of carbon tetrafluoride from methane and fluorine. So methane and fluorine are going to be our reactants. So methane is CH4, fluorine is F2, as you remember, as it's diatomic, and that reacts to give us carbon tetrafluoride plus hydrogen fluoride. Okay, and again we need to balance it. So we list our elements down the left hand side, carbon, hydrogen and fluorine, and then we write them in the same order on the right hand side. Then we need to count up the number of each type of atom that we have on each side of the equation. So how many carbons do we have on the left hand side? Just 1. How many hydrogens is 4, how many fluorines is 2. On the right hand side then we have 1 carbon, 1 hydrogen and 5 fluorines. So perhaps the easiest place to start is with our hydrogens. So we have 4 on the left hand side but only 1 on the right hand side, and so we can fix that by putting a 4 in front of the hydrogen fluoride. Now we need to update our list to change the number of atoms that big number 4 changes. So it affects the hydrogen and it affects the fluorine, so we need to change both on the list. So we now have 4 times 1 hydrogen, which is 4, And we now have 4 fluorines here plus 4 fluorines here. And so I now have 8 fluorines. Okay, so my carbons are now balanced, my hydrogens are now balanced, so I need to balance my fluorines last of all. And I have 8 on the right hand side, 2 on the left hand side, and so I can fix that by putting a 4 in front of my diatomic fluorine, because that's going to be 4 times 2, which gives me 8 fluorines. And now my equation is balanced, and I can write the final equation into my answer box. So it's 1 molecule of methane reacts with 4 molecules of fluorine to give me 1 molecule of carbon tetrafluoride and 4 molecules of hydrogen fluoride. Let's move on to part 3 now, and it asks us to use a dot and cross notation to draw the structure of boron trifluoride and carbon tetrafluoride. So it might help to write the formula of these compounds at the top, so BF3. And we need to think about what our central atom is. In this case it's going to be boron. And we need to look at our periodic table to see what group boron is in. So boron is in group 3. And so it's going to have 3 electrons in its outer shell. And so we will draw boron with its 3 electrons in its outer shell. 1, 2, 3. Okay, then we need to think of fluorine. Fluorine is in group 7. So it's going to have 7 electrons in its outer shell. So 1, 2, 3, 4, 5, 6, 7. Okay, so, but we have 3 fluorines, and each fluorine has space for 1 more electron here. It needs 1 more electron here. And so it will get it from each of these boron electrons. Boron will share 1 electron each with each fluorine. And so what we then produce is boron as our central atom. Let's take the top electron first. We'll then share it with a fluorine. But we need to draw all the other electrons around fluorine. And then we have 2 more electrons of boron, which will do exactly the same. So you can see there's 1 shared pair of electrons between each of the boron and the fluorine, and so we'll have 3 covalent bonds there. Now moving on to carbon tetrafluoride is CF4. So we're going to have 1 carbon atom and 4 fluorine atoms. So let's draw out carbon first of all. So carbon is in group 4, and so it's going to have 4 electrons in its outer shell. So I'll draw them as dots. 1, 2, 3, 4. If you find it easier to picture with the shell drawn, then feel free to draw the shell in. You can maybe see the position of the electrons easier. But again, it will do the same as boron trifluoride. Each of the carbons is unpaired, and so it can pair up with the unpaired electron of fluorine that we can see here. Okay, so carbon tetrafluoride, if we draw our carbon first of all with the 4, its 4 outer electrons. It then pairs up with the unpaired electron of fluorine, but then we have to draw fluorine's other outer electrons. And that's the case for the other 3 fluorine atoms as well. And so we have our dot and cross structure then for carbon tetrafluoride also.